Welcome to Google Cloud's digital conference. Let's talk AI. My name is Evren Eryurek. I am the Director of Technology for Analytics and Data Management on Google Cloud. We have Googlers on standby to answer your questions live, so please click on the icon to your left and ask away. We will be answering all your questions. I want to start with, if your company isn't good at analytics today, it's not ready for AI. You may have seen the study. Most companies, most customers who come to me and talk to us about analytics and AI, I want to first understand whether or not they are ready for AI. If they're not very good at analytics, they won't be good at AI either. AI is the new ground for gaining competitive edge and creating these new business values. As a student of AI, from my postdoctorate studies, AI is really generating this next set of deliverables, value adds to every industry, every user, every customer. What we're seeing in here is faster data-driven decisions, faster execution, faster insights from the data that you have that you didn't even know in some cases. If you notice, the operative word in here is faster, which is where the streaming comes to play. And you're going to see why that is the big focus for Google Cloud. We've been looking at streaming as the new big data trends. And look at the industry. Pretty much everybody is focusing on streaming and getting real-time insights from the data in hands. Batch has delivered and will continue to deliver a lot of value to many companies. But if you look at where the trend is, where the technologies are headed, streaming is where it is all happening. And we've been doing this in Google for a long time. Let's talk about that. As a business, everyone's objective is to gather the data wherever they are and bring it to a place, get some analysis done, and add some value. That data might be coming from your mobile devices that your users are using. It could be coming from the web searches and clicks that they are doing. It could be coming from the IoT infrastructures, from the devices, from the smart devices, or your internal data systems. Maybe your manufacturing plant, maybe your process control systems. The data is there, data is streaming, and our job is to really get that insight real time as an added value. On Google Cloud, we bring very powerful serverless streaming data analytics technologies. For ingest technologies, you have your Cloud PubSub. To transform them, you can use your Cloud Data Flow technologies, and you have your Cloud ML and BigQuery to do all your analysis for your tough problems to solve. Many companies have been taking advantage of these on Google Cloud. Whether they're in e-commerce or retail or gaming or manufacturing, they are using these very technologies. And these numbers are tens of thousands of companies. Every day, they're serving their industries, their customers. Let's talk about what you get from Google Cloud when you look at all the streaming technologies that we provide. You get a unified, open, and fully managed architecture for your streaming analytics needs. From your ingest to transform to analyze to visualize, you have them all. You can use our native technologies like PubSub and Dataflow, or you can use the open source technologies. As you know, we are a true believer of open source technologies. We contribute to the community and we partner in this community. And you know, Confluent is a big technology partner of ours, and they take Kafka technologies and make it easy for you to really leverage on Google Cloud and target your streaming needs that you're used to, maybe some of the tools that you're using on your on-prem solutions, and you want to bring to the next gen solutions. Those are all available for you as a managed service from Google Cloud. In conclusion, you have what it takes on Google Cloud to really deliver the next generation deliverables for your customers, for your solutions. Coming up next will be Kai and Jay talking to you on Confluent and what they're doing on GCP.
Thank you, Evren. Hi, I'm Jay Smith. I'm a cloud customer engineer here at Google Cloud, and with me today is Kai Werner, who is a technology evangelist at Confluent. Confluence, current Google partner, they provide a managed Kafka service hosted on Google Cloud. For those of you who aren't familiar with Kafka, it is a open source messaging queue. It's very popular, so popular that actually about a third of all Fortune 500 companies use it. And today we're going to talk a little bit about how to do that with machine learning, use Kafka with machine learning. So let's get to it, Kai.
Okay, thank you, Jay, and great to be here. Let's directly start with that and explain to you in 1 minute about Kafka in the end. It's an open source ecosystem, and we see it widely used for machine learning in the end. So machine learning is two things. It's training a model, and it's deploying the model for doing predictions, and you use Kafka ecosystem for that. So here you see in the end, for training a model, you use the historical data or real-time data from many systems like databases, applications, mobile apps, whatever, and then you store it in Google Cloud Storage, ingest it, pre-process it, deploy it there, and then you do your training of the model at scale. For example, with TensorFlow, leveraging TPUs on Google Cloud. And that's the one part, and then on the other side, you also have to deploy your model somewhere in production to do real-time predictions at scale 24/7. And for this mission-critical system, many use Kafka and Confluent open source ecosystem to do that. And we have Confluent Cloud to host that in Google, so that you can do all of that at scale without managing the Kafka ecosystem by yourself. Here you see this part where we get all the data from somewhere else. In this example, what we often see, we have Kafka clusters also on premise to get all the data from assembly lines, from connected cars, whatever the use case is, get it into Confluent Cloud and process it there. As you know, as data scientists, for creating models, you have to do things like pre-processing, filtering, enrichment, target featuring, engineering, and all these things. That's done with Kafka and its ecosystem, and then it's stored in Google Cloud Storage to do the training with TensorFlow or other machine learning frameworks. That can be done, for example, with Google ML Engine. And then after you have your model, you have to deploy it somewhere, either in the Google Cloud or somewhere else, like, for example, on-premise, if you want to do local processing for PII data. In this case, we also have a self-managed Kafka cluster with Confluent, where we leverage all the technologies like Kubernetes also. And this way, you have the benefit of having the same infrastructure in the cloud and on-premise, so that you have to build your pipeline once. You have the pipeline for pre-processing the data for training, and then also for deploying the model and doing the predictions for that. Here you can both do with Kafka at scale, with the same benefits like failover, high scalability, and all these things. And also pick what you choose. So just use the things you need, both true for Kafka and Confluent ecosystem and for Google Cloud, right? And this is the combination you want to do. And with that, you can deploy Kafka with two different options for machine learning, either model serving in a TensorFlow serving, like on Google ML Engine, or on-premise. And this is the one option. Here you do request response with gRPC. And on the other side, if you don't want to use the side effects of another server, then you can also use TensorFlow embedded into Kafka Streams or KSQL. That's the two options, both with trade-offs. And now let's think about how to do that in a real-world example. With that, let's take a look at this mission-critical use case, payment fraud detection. Here we have local data from cars and feed it into the Kafka cluster. And with that, we do our processing on that, in KSQL in this case. And here we apply the analytic model, which I have embedded into the KSQL function, as I will show you in the live demo. And then we will get the result, the prediction, and forward it to a big data storage like Elasticsearch for search, or the filtered predictions for potential fraud to an emergency fraud system. And that's in the end the use case I want to show you now in the live demo. I'm here in the browser, though this is my GitHub project where I built such an example. You can go through that step by step. And in this case, I already use a trained model, which we have built in the cloud before. And now we deploy that to production. So here again is the GitHub project where you see the same use case. And now I simply go through that and show you how the model is used. So for that, we have to go to the command line where I have already started a Kafka cluster. So it's a local one. So let's see here, Confluent status. I use the open source command line interface to start Kafka locally for development and testing. And here we see we have Kafka, including its dependency started, and also the KSQL server. So this is a good first step, and now we can use that to show you the demo. For that, I really go step by step through my example on GitHub. And with that, you can do it in the same. It's really a running example. And if you have any issues, just create an issue on GitHub. But it should work. It's tested many times in these kind of demos. So as first part, we create a Kafka topic. This is used here, temperature, to get data from sensors into the Kafka cluster. With that topic created, this is in the end where we ingest the data from the devices, right? And then we can continuously process it in real time at scale. So I have already done the configuration. And in this case, I'm using the MQTT proxy to process sensor data. So I use it here. This command starts it locally. And of course, in the real world and later in development for clusters, we would use Docker containers and deploy it in a local Kubernetes cluster. But in this case, on the laptop, I'm just using the command line interface to start this. We now have the MQTT proxy ready, and this is waiting for sensor information and forwards it directly into the Kafka cluster where we can process it at real time. And this might look simple here because I only start a few processes, but of course, as you know from Kafka, this can be done at scale, both in the Google Cloud or then on-premise in a cluster. Let's go here, and now what I also start is KSQL. KSQL is in the end a processing engine on top of Apache Kafka. So no additional big data cluster needed, just use small processes. And here you can write SQL queries, so you even can do stream processing without writing source code like Java. And that again at scale. You can start in the Google Cloud, hundreds of instances on top of Kubernetes, for example. And so here with KSQL, I am now writing one query for a stream. This stream is now collecting the sensor data, which we send from the edge devices, in this case connected cars, via the MQTT proxy into our Kafka cluster. And so here we now see we are waiting for data, and now we can create a query. So let's take a look at one of these queries. I just use here one query. It's a pretty simple query. It selects the event ID from the sensor and uses one function. In this case, it's a UDF, a user-defined function, where I embedded the TensorFlow model, and there where the story emerges again. So here we get the sensor input inside this function here and apply the analytic model. Mm-hmm. So the TensorFlow model, which was built in cloud at scale with TPUs and terabytes of data, is now used at the edge. And this actually can run even on a Raspberry Pi, for example, right? And can do real-time processing and predictions of the TensorFlow model. So the implementation under the hood, and you can also take a look at the code, it is a Java UDF which embeds the TensorFlow model here. And then it gives you an output. In this case, we use an autoencoder to find anomalies in the payments based on the historical data at scale from the Google Cloud. And so now let's create some data to show you that. Here we use, in this case, Mosquito client. So this is just one MQTT client. It doesn't matter. It simulates devices which send data, right? And now when we send this information, here you see it's sent to the topic car engine temperature. This is the MQTT topic. And the configuration under the hood maps this to a topic in Kafka via MQTT proxy and sends it to the Kafka cluster. So let's press return here. And as you see at the top, the MQTT proxy in real time forwarded it to my KSQL stream process. As soon as I click, let's do it one more time, you see in the middle, the data is processed in real time and it outputs a prediction. So the 9999 is the ID and the prediction is the number here. And so let's do one more thing, because this is just one number. Let's use a sensor generator which simulates real-world data. And so here, continuously around every second or so, it creates random data sets, which shows you input data and the applied function of TensorFlow to show you anomalies. And this is in the end how we use the trained model from the cloud at the edge using Kafka streams or KSQL. And again, this can be at scale, even though this is just a laptop deployment. But typically, we would deploy it on Kubernetes, for example, in Docker containers, then scale it up and down, even at the edge. And now, when we have this demo finished here, let's think about this again as last part, where we go back here to the use case. Now we're getting all this data. This is what I showed you. And now we are sending all the data somewhere, like an Elasticsearch, or we could create another KSQL query and filter, for example, the critical alerts. Let's assume, going back here, that the anomalies is everything over 4.5. So this could be the potential fraud. This could be sent on a real-time system, alerting system, where we send only this data to. And there someone can react critically in a few seconds or minutes to decide if this payment is accepted or not. And this is how the story is completed, because then afterwards we go back in the end to the cloud, because this is just the first use case we set up. And then we have to retrain the model, we have to get new data in it. And with the pipeline we have built before, we can retrain the model in the cloud with TensorFlow, with new terabytes of sensor data from many different cars, build the improved model, and deploy that again to on-premise at the edge. And so that's, I think, a very good use case for showing how to use Kafka and Confluent together with TensorFlow and together with Confluent and Google Cloud, because here you really see the advantage of doing it at scale in the cloud. And one last note, of course, you can combine and pick the scenarios which you need and the components. So either like here, we use many of the Kafka components like KSQL, Kafka Streams, Kafka Connect. But also you can integrate well with other things besides Google ML engine. So for example, if you want to do image detection, you could directly integrate with Google's image recognition service, where you don't train the model by yourself. So you can do it really, pick and take what you need in the end. And that's a great story and why we see so many people using Confluent together with Google Cloud and TensorFlow.
Right, yeah. I mean, it requires a lot of data to do the training. And then, of course, you're going to, once you're trained to do the prediction, you still collect a lot of data. So Kafka is great at queuing that up. And then, of course, you can use Google for the actual training.
Exactly.
Well, thank you very much, Kai. Up next, we have Sergey, our PM for Dataflow, and I will send it off to him.
Thanks, guys. My name is Sergey Sakarenko. I'm a product manager on Cloud Dataflow. We just heard how streaming data is used during model serving. But to get to model serving, you have to first train your model. What we're beginning to hear more and more from customers is that they're using continuous model training, where streaming data is actually also used to refresh your models. Here's how it works. As your stream gets ingested, it's being persisted in a persistent data store or in the state of your data processing framework. You then want to run this micro batch of streaming data against a schema, just checking that the types of fields that you're getting correspond to your expectations. Sometimes you also want to check these values, field values, against distributions you've seen in the past. After validation comes the transform phase, when you have the needs to transform your feature columns from strings to integers, or when you're converting float values to z-scores. You need to do a full pass on your data set, and this is where transforms come into play. Once you're done with validation and transformations, you're now ready to retrain the model. You'll probably use a hyper-tuning tool to slightly modify the parameters of your model to achieve the best accuracy metrics. Once you achieve this optimum and maximum, you're now ready to run a quick QA pass, making sure that the model is safe to serve and it doesn't create embarrassing predictions on edge cases. You're going to push this model to a serving location, and you're going to begin serving predictions. We're also seeing customers doing more and more incorporation of user responses to predictions into the next cycle training exercises. In addition to user responses, they also sample serving logs and use them to detect skews between the training data and the actual data they observe in streams. When you look at a real-world ML production system, you quickly realize that all this additional functionality that you need in addition to the machine learning code becomes daunting. And so we at Google have been working on a production-scale machine learning platform that is based on TensorFlow and provides the additional capabilities that users need. For example, all the boxes that you see on this chart today are available. And you have your TensorFlow data validation, you have your transformation features, you have the model serving capabilities, and the TensorFlow serving feature. This platform is called TensorFlow Extended, and we are continuing working on remaining pieces of functionality. 3 of these capabilities that I just mentioned are using Apache Beam to do a distributed data processing exercise. For example, when you have a string column and you want to convert it into integers, in the process creating a vocabulary of your strings, you have a feature now to run this processing exercise on Cloud Dataflow in the Google Cloud. And when you do that, Cloud Dataflow will create hundreds, if not thousands, of workers that will do the transformations quickly and efficiently. I mentioned a couple of terms just a few seconds ago, Apache Beam and Cloud Dataflow. Let me explain the difference. Apache Beam is an open source programming model. It provides exactly once streaming semantics, and it has a very nice API that allows you to write both batch and streaming pipelines using the same API. Now, Cloud Dataflow uses Apache Beam as the SDK, but it's a fully managed serverless service provided by the Google Cloud. One interesting and great quality about Cloud Dataflow is that it is able to automatically scale from just a few records per second to millions of records per second, which comes especially handy when you have a streaming use case. Now, one of the problems that Apache Beam and TensorFlow Extended allows us to solve is the training serving skew. What is this training serving skew? The skew is being created when you use different technologies during training from technologies you use for data transformations during serving time. And that happens because during training time, when you're focused on highly efficient batch processing, you will use a different tool set and different languages and libraries to pre-process your data. During real-time serving time, you will use yet another set of real-time technologies that efficiently pre-process data. And so because of this difference, you're creating differences in ways how your raw features are being processed, which impacts the accuracy of your models. With TensorFlow Extended and Apache Beam, we are now able to solve this problem. Let me explain to you how it's being solved. Let's imagine you're starting with a raw training data set. You can use the TFX TensorFlow Extended Transform library that will run on Apache Beam to create two artifacts. One of them will be the transformed training data. For example, all of your string values will be replaced with integers. All of your float values will be replaced by z-scores. And you can also apply some bucketization algorithms to create buckets instead of discrete values. But in addition to transform data, you also get something that other tools do not create, and this is the transform graph. The transform graph is a TensorFlow graph that you can use during serving time to process your inference request in the same fashion as your training data gets processed. Once you have transformed data and the transform graph, you can now run the TF estimator libraries or your Keras model and create the inference graph. And together, the inference graph and the transform graph enable your serving infrastructure to apply the same transformations on your streaming data that contain inference requests as you apply during training time. The result of it are predictions that are much more accurate than in the past. Let me do a quick demo of how these concepts work together to provide a production scale machine learning system. In this demo, I'm going to use the Chicago taxicab data set that the city of Chicago has been updating since about 2013. In the data set, I have information about each taxicab ride, such as time of day, the start and the end point of the ride, and the amount of tips and fare that was collected during this ride. Now, if you are a taxicab company, one interesting question you might ask yourself is, can we do a prediction? Can we predict whether a particular taxicab ride will result in an above average tip? And the reason why it's interesting to know is if you're caring about the equitable wage distribution of your drivers, you might want to dispatch your taxicab rides such that your drivers get equal opportunity for earnings. So in the demo, I'm going to use my BigQuery data set, and I'm going to read this data set into a Cloud Dataflow pipeline that will run a TF transform job. This job will create two outputs. Our first output will be the transformed training data. This data set will contain all of the float values converted to z-scores, all of our strings converted to integers, and some columns bucketized and presented as bucketed features. Now, the other output will be actually a transform graph. And what this means is it's a TensorFlow saved model that you can use together with an inference graph during serve time to transform your inference requests. Once we have our training data and our transform graph, we can run our machine learning job and do a training exercise. And we're going to do this in this demo in the Cloud ML engine. The training job will produce an inference graph, and we'll deploy this inference graph into, again, CloudML engine. And together with the transform graph, it will enable us to take raw inference requests, a stream of taxi cab rides that we get. And we will take these raw requests and we'll transform them first into more usable requests, and then run online inference on them, resulting in predictions. Our predictions will be very simple probabilities. Is a particular taxi cab ride going to result in an above average tip? Let me show you the BigQuery dataset that contains the 37 million taxi cab rides. The table taxi trips contains information such as the ID of the taxi, the start time of the trip, the end time of the trip, as well as the fare info, the amount of tips, and the location of the pickup point and the drop-off point. So with this data set, I have launched a data flow job, and the data flow job ingested the data from the BigQuery training data set and processed 37 million rows, about 15 gigabytes worth of data, and it had two outputs. In my first output, I created a transform graph. And this graph is a set of files in a GCS bucket that represent a transformation graph that I can then use for serving and training. In my other branch of the outputs, I actually transformed each of the 37 million rows and created transformed training examples. As you can see, I got 37 million outputs, and this information actually did expand somewhat to 18 gigabytes worth of data, because now I have additional columns that store my z-scores, my integers for the string columns, and my bucketized columns. The outputs we've written into GCS storage. Here's the bucket which received these outputs. The Cloud Data Flow job created 133 files containing my transformed training data. And if you scroll to the bottom of this GCS bucket, you will actually see a directory or a folder called transformed FN, and this is where my transform graph is going to end up. All right, so far we've ran our TF transform, we pre-processed data, we created training samples, and we created a transform graph. Now we can go and run a training job, and we're going to do this training in the CloudML engine. I did a run just a few hours ago, and this particular run was successful. It ran for about 26 minutes, and it used as inputs my training data as well as my transform graph, and it produced an output directory with the inference graph. So now I have my inference graph, I have my transform graph, and I have a stream of inference requests which are nothing else but information and events related to taxi rides. They contain attributes such as the start of the trip, the location of the pickup, the intended destination, as well as payment type. And what I'm trying to get out of it is a prediction, a probability number that will represent the probability whether a particular ride will result in an above average tip. So for that, let me go and actually show you how to do model predictions. I deployed my models just before the demo into the CloudML engine, and now I have a model that can serve prediction requests. This model receives a fair amount of predictions per second. I'm getting pretty good rates here. And if you look at the latency of these predictions, they are actually great. They are all below perhaps a dozen milliseconds. So it's a quite efficient way of doing predictions. Hopefully I was able to quickly show you the power of TensorFlow Extended and Apache Beam as they work together on ensuring that there is no training and serving skew. If you would like to learn more about this example, please check out our GitHub repository under TensorFlow Model Analysis. Look for the Chicago taxicab dataset and example set. I would like to thank you for joining us today and your attention. Please stay tuned for the next session. I hope you're enjoying the conference.